Welcome to the tutorial for NPTEL course, Programming Data Structures and Algorithms in Python by Professor Madhavan Mukund. I am Jivesh Dikshit, basically teaching assistant for this particular course, and I would like to welcome you for the uh, week 1 tutorial. As you all know, week 1 material is already out, and this is basically related to that. The idea of tutorial is to help you with the uh, practicing problems, and if you're facing some issues and everything. So I have prepared some problems. I'll show you, and we'll see how we can proceed to solve those problems in Python. So first of all, first problem will be looking for, we'll try to list all the numbers that are below a given number n. So there can be various approaches to list all those numbers, and it is important for us to know what could be the uh, more efficient approach to solve the problem, because for smaller numbers any algorithm may work for you, but as the numbers become larger and larger, then the computation becomes costlier for the inefficient algorithms. So for example, for this, the most efficient approach I have mentioned here. So basically, this is known as Eratosthenes algorithm. But before that, we'll see that how else we can proceed to address this problem. So first of all, what we can do, if we are already given a number n, we can check all the numbers that are I mean, we can check all the numbers between 2 to n, because the prime numbers are the number which are not divisible by any number other than 1 or itself. So we can check whether it is divisible by number 2 to n minus 1. So n is the number given, so we'll check up to n minus 1, because of course it is divisible by n. uh, so for a given number n, once we can check whether it is divisible by any other number between 2 to n or not. If it is not divisible by any other number between 2 to n minus 1, it will be a prime number. Then, but we want to list all the prime numbers that are below the given number n. So we can proceed it with the same idea. Then we can apply the idea on n minus 1. So in this case, we'll be checking whether n minus 1 is divisible by numbers between 2 to n minus 2, included both the extremes. Similarly, we can check for n minus 3, n minus 4, and so on. So this is the idea, but this is not a very efficient algorithm, uh, and we'll see that how inefficient it could be for larger numbers. So so all the computations basically for this particular course I'll be doing on deepnote.com. So it is basically analogous to Jupyter Notebook, if you people are aware about. So basically, in Jupyter Notebook, we have different cells, and these cells can independently run. If we want, we can run them independently. Okay. So first of all, the approach we have discussed is the most basic approach. In most basic approach, we'll be checking whether the number n is divisible by all the numbers between 2 to n minus 1, including all the extremes. So here we have, if we look at the function defined here, so we want to check whether we want to check whether the number is prime or not. So we'll be checking for n less than or equal to 1. We can see here we have put a condition. If n is less than or equal to 1, so by definition, uh, a prime number it has to start from 2. First prime number is 2, and then on we can have the prime numbers as per their definitions. So any number that is equal to 1 or below, it cannot be a prime number. So we if a number provided in the function is equal to or less than 1, we'll straight away say that okay, there's a, I mean, the function is going to return false and it is going to terminate. But if we provide a right number that is between 2 to n, then our basic approach, according to our basic approach, we apply a for loop here. What for loop says, for I in range 2 to n. So basically range is a sequence in Python. So when we say range 2 to n, so it takes values 2 to n minus 1, because according to the syntax of range function, the first number here basically is the start of the range. Second number is the is the point where we need to stop, and there is a third number defined as a step. So as we have not given any step here, in default it will take it as 1. So now, so this range will run, it will not run from 2 to n. In Python, the indexing basically starts with 0. So, and it, when we say index 2 to n, it goes from 2 to n minus 1. Or if we say 0 to n, it goes to 0 to n minus 1. It does not include the last, it is not equal to the stop number. It is always lesser than the stop number. So now if we check in the next line, we can see we have applied a condition here. If n is divisible by I equal to 0, so sorry, if n modulo I equal to 0 means if we divide n with I that is ranging from 2 to n, so if it is divisible by any number in that range, it means the modulo is 0 or remainder is 0. So it means the number is divisible by uh, divisible by other numbers than 1 and itself. So in that case, we can say it is not a prime number, so it would return false. But if after running this loop completely, so we can see in Python the indentation plays a very important role. So basically, if we see this function here, def prime n is basically, it is defined by this total block. So this block is basically understood by Python with these indentations. So we have started our definition here, but when we give our instructions, we just give it, I mean, by some spacings or tabs. But we need to be very careful while giving the spacings or tab. uh, by saying, if let us say first statement you are giving first statement you are giving with the indentation, let us say 2 spaces or maybe 1 tab, so you need to be consistent for the same level of indentation. However, if we look at this, if n is less than 1, so we have defined a condition. So in a way, we have defined a nested block. So in case of this nested block, we have given a further indentation so that Python knows that inside this if statement, this particular instruction comes, and as we move out of the indentation, we know that this line does not come under this if statement. So we need to be very careful about the indentation. They actually define the blocks in Python. So like in other languages, you might have seen that the blocks are defined by curly braces, but here blocks are taken care by indentations. So now, so as we have come out of this for statement, if n is not divisible by any number between this range 2 to n minus 1, so if it is not divisible, hence it means that it will be divisible by 1 and itself. So we will return it to be true. But this function basically tells us about if a number is given, whether that number is a prime or not. So we can see it is returning either true or false. So basically it is just returning us some boolean output. So either it is saying okay, our function is prime, or it says it is not. So, but now we want to calculate all the prime numbers that are below n. So for that, what would we do? What would we do? We will we will define the number we want. We will initialize with a number. So let us say we want to calculate all the prime numbers that are below 50,000. I have taken this large number with some intent, and we'll see why I have taken this large number. We can take even the smaller numbers so that our computations are faster if we are just checking how the algorithm works. So basically, I have initialized with n number is equal to 50,000, and now I will check for I in range 1 to num plus 1. So I would like to check whether whether I mean what are the numbers that could be that could be prime. So we'll see, we'll run this. So basically we are saying that in range 1 to n plus 1, or in our language maybe we can simply say I am checking the numbers 1 to num. So num here is 50,000. So we are checking numbers 1 to 50,000. Whatever are the numbers that are prime, we will uh, we will uh, we will print them, and if the number is not prime, we will avoid printing them. So this is how we will know that numbers uh, how many numbers and what numbers are prime below the given num. So if we see, I have after running this, after giving this iterative loop for range 1 to num, if number is prime. So you should remember that our function prime num was returning whether our number is prime or not. It is just returning true or false. So here we are applying a condition if prime num I, and we are not giving any condition after that. So it means if prime num I is equal to true, then the following condition or the following instruction will run. If not, it will come out of this if condition. So then if our prime num I is true, we will simply print I. Now so basically this is the total this is the algorithm. This is our function which we have defined, whether to I mean to check whether our given number is prime or not. And here we have run a condition to check all the numbers that are below a given number whether they are prime or not. So basically this is called uh, a driver block or driver uh, instructions. So now I have here intentionally have done one thing, which it is just to show you that how efficient or inefficient an algorithm is when we compare it with if you can see, I have for problem one I have chosen three approaches. So we'll see that which approach is how much I mean efficient. So for comparison, what I have done, I have imported a library. So if you do not know about these libraries or modules, you need not to worry. So basically, this is a library. It's an inbuilt in Python. So what I have done, I have imported what this library would do wherever in the code. I will write it like time.time in and parenthesis. It will start the time from there. Okay, it will give us the time of start of that particular line, and wherever we again put it, it will give us the start of I mean the sorry, here it will give us the end of this particular line in terms of seconds. And similarly here also it will give the here also it will give the end of this particular line. And this is how, if we take the difference of these two, we will come to know that how much time is taken by this particular program to run. And that is why I have chosen this number to be very large, and we'll see if we decrease this number, then the algorithms may be approaching towards each other in terms of computational cost. So I will run this function. So this function is now defined. So basically it is just a startup kind of thing. Okay, so it's ready now. The function is run. The function is basically in the memory. So now we'll see how much time maybe this particular block is going to take, or this algorithm is going to compute all the numbers, prime numbers below 50,000. So if we run this, it is computing. Uh, so okay, so it has taken 9.8548 seconds. Okay. For next approach, now we know that the number n, it cannot be divisible by number which is greater than n by 2. So if we have number 3, it cannot be divisible by by number that is greater than n by 2. Okay, so like if we choose 4, so 4 cannot be divisible by 3. So so this is how with this approach we can decrease the number of iterations. So because earlier we were checking for all the numbers 2 to n whether our number is prime or not. But in this case we need not to check all the numbers. I mean, if they are dividing n, to check whether the number is prime or not. So as we have discussed, any number cannot be divisible by the number that is greater than n by 2. So if n is the number we are choosing, it cannot be divisible by number greater than n by 2. So in that case, here we will everything will remain same. We will say that okay, if n is less than or equal to 1, we'll say that okay, this cannot be a prime number. It will, the function will return false. Now so we'll check for if the n is given as a proper number. So like if n is given as a minus 256, there is no point checking. So it will simply say, okay, the number is not prime. So if number is greater than 1 and it is an integer, so in that case we'll be checking whether it's a prime number or not. And here in our algorithm we have made some changes. Now we are looking from the range of I from 2 to n double slash by 2. This double slash basically represents the floor division. Floor division is nothing but it's a greatest integer function. So basically if we divide 3 by 2, 3 double slash by 2 will get 1, or we'll divide 5 double slash by 2 will get 2. So uh, so basically for I in range 2 to int n double slash by 2, or floor division plus 1. So we are considering numbers up to n double slash by 2. So that is why we have added plus 1, because the step is taken 1. So if our stop is going to be one number lesser than this, so we will get our stop number as int n double slash by 2. So now we'll check for all the I in this range whether n is divisible or n is divisible by I or not. So if the remainder is 0, means n is divisible. So if for any I in this range our n is divisible, the function will return false, because our number is not a prime number. Otherwise it will return true. So we can see that here we have decreased the number of computation just by decreasing the range of this particular checking checking instructions. So now here also I have called this library time. I have set the start time, I have set the end time, and we'll see that how much this end time minus start times comes out to be. So here also we have taken this number to be 50,000. Uh, we'll check for all the numbers up to 50,000 whether I mean we'll check for all the numbers whether they are prime or not. So if they are prime, if they are prime. So basically, as we have already discussed, if we do not give any condition, it simply means whether this is going to return true. So if this is true, this instruction will run. If not, our interpreter will come out of this particular if statement. So that we have already discussed. So basically, in this case, if uh, let us say if I as it is starting with 1, so we'll check for 1, we'll check for 2, 3, 4, and so on, and we'll see whether those numbers are prime or not. If prime, they will be printed. If not, they will be let go, so we'll not print anything. So this is how whatever will be printed will be a prime number, and we'll check how much time this particular code is going to take. So we can see this has taken 5.748 seconds. So which is somewhere, around half the time that our earlier function has taken, because we have decreased the number of steps for the computation. Now, the next approach we can think of, this is called, this is another, it's a more efficient algorithm. So why it is more efficient, it's it's very interesting to see, because our first prime number is 2, second prime number is 3, third prime number is 5, fourth is 7, and so on. So then fifth would be 11, and the list will keep on growing. Now we can say for sure that any integer multiple of 2 is not going to be a prime number. Any integer multiple of 3 is also not going to be a prime number. Any integer multiple of 5 and 7 and 11 and so on is not going to be a prime number. But while calculating those prime numbers, if you observe, while we are calculating the non-prime numbers that are multiple of 2, it would be 4, 6, 8. Mind you, if we are if we want to calculate the non-prime numbers that are multiple of 3, it would be 6. Now we have already calculated this number 6 while we were while we were looking for integer multiples of 2. Similarly, as we will moving on, we will see that many numbers are being calculated multiple times. Okay, so in this algorithm, what it does, a number a number cannot be divisible by uh, it cannot be divisible by a number that is greater than root of n. So square root of n. So that is a definition. So, and for that you can simply make a chart, maybe from number 1 to 100, and you can check. So uh, I mean, you can let us say, if we say 49, so 49 root is 7. So if 49 is not divisible by 7, I mean, uh, I mean, we are calculating the integer square root. So basically, if we say 50, so 50 is 50 will be divisible by, let us say, uh, uh, I mean, if we calculate the square root of 50, it will be for 7 point something, and if we calculate the integer value, it will be 7. So 7 is the closest prime. I mean, it is the square. If it is not divisible by numbers that are lesser than, equal to, or lesser than 7, hence it will not be divisible by numbers greater than that. So it is one of the theorems you can check by just making a table, and then you can process. So basically, this algorithm, we can see it further reduces the number of iterations that we are going to use for the uh, for the computation whether our number n is a prime number or not. So in this function also, if we see, only the range has changed, range has been decreased. So with this decreased range, we'll check for all the i's that are in this particular range, that is 2 to uh, uh, 2 to integer square root of the given number. And if that is true, the function the number is not going to be a prime number. And if for all the numbers in this range, if n is not divisible by any number, then it will return us true. So now this function is same as the functions we have already seen. So but only the definition of the function has changed. The driver instructions that are same. So basically we can see the number, again we have chosen 50,000 just for the sake of comparison how much time it is going to take. So we'll run this, and then we will run this. You can see it has taken less than 1 second to compute. So basically, as you have already seen in the course, that uh, how we define or plan our algorithm, it affects the efficiency of our computation. It may not appear to be very meaningful when we are dealing with very small computations, but with large computations, you can see that these these calculations or these algorithms, more efficient algorithms become more meaningful. So just to show you one example, if we decrease this number, let us say I'm going to decrease it to 500, and I'll need to run this first because the name of the function is same. So okay, so it has taken 0.0159 seconds. The next one, we'll see how much time does it take. Okay, so sorry, I forgot to change number here. Okay, so we can see this has taken 0.0119. Earlier it was taking half the time, but right now you can see the difference is not too much. So for smaller numbers, it may appear that the difference is not much, but as the computations become larger and larger, the difference appears to be much more prominent. And here we can see that the difference to be more prominent, but between these two the difference is not very much when we compared in earlier case. So basically this function I will not be using further even if I will be comparing two algorithms, but I think you got an idea that if we change the algorithm, how our computational efficiency is going to improve, and that is the idea behind this particular course. So okay, so we have seen this, and here I have given you the approach. So I think you will be shared with this these slides and everything, so you need not to worry about, and the videos will also be shared. So okay, so next problem we'll be looking for calculating sum of cubes of the digits of a given number. So let us say our number is 153. So this function which we are going to define, it is going to it is going to calculate the cube of every digit. So in 153 it will calculate cube of 1, cube of 5 and cube of 3, and it will return us the summation of that particular number. So basically for that if we see the in our algorithm, we are going to first define a function which is going to calculate the exponent of number. The exponent is basically, it's nothing but a power function. So either we can define our own function, or power actually it's a inbuilt function in Python, and we'll see it in a bit. So power, it's a inbuilt function in primitive Python that you get from python.org. So basically, we can use that function in place of this if we don't want to complicate our efforts. Then we will you know we will we'll see that then we need to be careful that the numbers, as here the idea is just to calculate the sum of cubes of a given number. So we'll be choosing numbers that are the whole numbers that are positive. We'll not be choosing negative numbers here. So I will see that we can even to make a more interactive code. So let us say you have written a code, but the someone you are giving it to someone else to for their utilization. Then sometimes it's better to write some comments, or when there is an issue, throw some warnings or errors. So we'll see that how we can throw a simplest way to throw a warning, or the error kind of thing. So we'll not go into how to throw an error, but we'll see. It's a very simple way to return a warning with the termination of the program if some garbage input is given by the user. So like in earlier program, we have defined the number n inside the program. What we else could have done, we could have asked the user, while running the program, we could have asked the user to input a number on their own. So that has its own perks. So we'll see maybe in next program. So with that, we'll be proceeding with calculating the last digit. So basically, we'll simply use a modulo function, and we will divide it. We will divide the number by 10. So let us say we have a number 153. If we divide it by 10, so modulo will be 3. So this is how we'll get the last digit uh, of the number. We'll calculate the cube of it, and then, and in parallel we'll also update the number by dividing it by 10, and I mean and returning it as an integer. So what I mean is, for 153 we'll calculate the modulo, we'll get the remainder 3, we'll calculate the cube, and in parallel we'll replace our number with number divided by floor division 10. So if we do the floor division of 153 by 10, we'll get 15. So now we'll proceed with the same procedure. Then we'll give the last digit to be 5, and finally we'll get 1. So we'll calculate the cube of all those, we'll calculate the sum, and then we'll finally get the sum of cubes of all the digits. So this is the idea. We'll try to see whether we are able to implement it efficiently. So here in the first line, sorry, this is a function where we define, this is an exponent function. What it does is it basically returns x raised to the power y, and in place of this function we could have simply used an inbuilt function, that is pow x comma y. So let us say for now, uh, okay, so after defining this, maybe this exponent function, so for here, actually we have used recursion basically here. Recursion, I think you guys have not studied yet. So basically in recursion, it's like a induction. So what we are doing is we are giving some condition, and after processing that condition, we are returning something. But here if you see, we are returning a function with the updated inputs. So now the function will again run with these updated inputs, provided this condition. So this will keep computing until our the final finally computes the power of x comma y. So don't worry about the regression thing. It will come in future. So for now, if you're not comfortable with this until you learn the regression, you can simply use the inbuilt function here. That is pow x comma y in place of exponent x comma y. Okay. So now, as we have already discussed, we were interested in calculating the sum of cubes of the digit. That is our primary motive. So and this inbuilt function is already there. So what we are going to do is, first of all, we are simply that, this thing we could have done in last program as well, but don't mind. uh, we'll be seeing here how we can proceed with such things. So what we would say is, we will say if type of num, so type basically is an inbuilt class in Python. What it returns you, it returns, it's an inbuilt function in Python. What it returns is, it basically returns the class associated with this num. So as I think you people are already aware that there are basic inbuilt classes. There are integers, floats are the number with floating points that divide the whole number and the fractional part. So for now, as we want our number to be integer, because then only it's meaningful to calculate the sum of all the digits. Because for some case, if even if we want to calculate the sum of even the fractional part, if maybe given, then it will complicate things a bit. Because then there can be a possibility of irrational numbers that will extend up to infinity, and so we don't want to go into all those complexities. For now, we just want to learn how we can proceed with the algorithm. So first, we are simply saying that if the type is, maybe if you are supplying a garbage data, you are not providing a type. Then this for num, you are not providing an integer type, or you are providing number less than 0. So in that case, what our function is going to return, it will simply return, please provide a valid integer. So we could have even omitted this print statement. So nonetheless, you can remove it, or you can let it be there. It won't make much difference. Then if assuming if proper input is provided, if proper number is provided, so let us say a number is provided, that is 1, maybe 10, maybe 100,000, maybe 1563, maybe 999999, and so on. So if such numbers are provided, the proper numbers, so if this does not return an error, or the proper number is provided, then we'll move on to a statement where we will simply say if num is greater than 0. So we'll see why we are calling this num is greater than 0. We'll see that we are first computing the modulus. So basically, the modulus will be the remainder when num is divided by 10. So num is divided by 10 if, as we have already discussed, if our number is maybe 37. So if this number is divided by 10, the remainder will be 7. So we will get the last digit of our number. So we can calculate the cube of this using this exponent function, or we can simply remove it, or we can call the inbuilt function power. So whatever you use. So if you can see, if when we have written this power, this the color is a bit different. So anyways, you can try that, no issues. So this is a user defined function. It's not coming in bold and colored, but the inbuilt functions are coming in bold and colored, as you have already seen, this def and type and everything. So basically this type of uh, i mean uh, IDEs or integrated development environments, basically they help us to they help us write a code with more ease. Like here, if if we have defined a function, there is a colon. So after colon, whatever instruction you want to give, they should start with an indentation. So if I put enter, it is already indented. It has not reached here after pressing the enter. So it has gone to a new line, but it has gone to a new line that is defined by a tab. Okay, anyways, so here first of all, when everything is right, we'll calculate the modulus, we'll calculate the cube of the modulus, because we want to calculate the cube of all the digits in the number. So I mean now uh, as this is a loop, so if we do not, as this is a loop, so every time this modulus is going to be updated, because this number is going to be updated. You can see the number is again defined as floor division of number by 10. So it's nothing but, as we have discussed, it will return us the integer value when greatest integer value when divided by 10. So uh, if we do not if we do not initialize our value and we keep on adding, then what would happen? This value that is with, because mod is going to change every time, num is going to change every time, our exponent value is also going to change. So we cannot do it like we can compute first and then we can add later, until we store it in some some other sequences. So we are not going into that for now in lists or maybe other things. So for now, we'll see that we are initializing this, we'll initializing this variable here. We are calculating the modulus. We are computing the cube of the modulus. We have initialized it with 0. So we are saying that this variable is equal to the variable again which has value 0 plus whatever cube of digit we have calculated. So now our value of cube sum digit has become exponent mod of exponent of mod comma 3. So now our number is updated. Our new number is floor division of number by 10. So our number is updated. We'll again calculate the modulus. So if we try to divide 5, let us say our number is 57. So 50 in first go, it will be our modulus will be 7. So here it will be 7 cube, and our number will be 5, because 57 by 10 will be 5.7, and we, as this is a floor division, it will return us the greatest integer, so it will return us the 5. So our new number will be 5. As it is greater than 0, we'll again run it. So if we divide the number by 10, so the remainder will be 5, because 10 times 0 will be 0, and 5 minus 0 will be 5. So next number returned will be 5. When our the value of cube sum digits is updated by 7 cube. So this again will update this value by 7 cube plus 5 cube. So we'll get the our number that we are intending to get. So now this is a garbage value. You can see the -2. By saying garbage, we have mentioned our program. Okay, if it gives you these kind of values, you just please tell the user that please provide a valid integer. So user will know that it is a warning. If it does not produce a warning, it throws some error or something, it would be troublesome. So it is always good to write a warning in a sense that a user easily understands. So we have run, okay, when it's -2. So we have improved it by saying, okay, give us a number that is, please provide a valid integer that is greater than or equal to 0. So we could have said that. So but if we define in place of this -2, we are going to define maybe some other kind of class that is not an integer. We'll see what it returns. Okay, again it is saying please provide a valid integer, because we have already given a condition. If type of number is not integer, you should return this warning. If type of number is less than 0, you should return this warning. So in those cases we have got the warning. So now we'll check maybe for number 203. So it's easy to check. Okay, so it's 35. So 27 plus 8 is 35. That seems fine. Maybe if we change a number, we say, let us say 153. Okay, so we got in value 153. Summation, you can check, it will come out to be same. We'll say 9474. We'll run this again. We'll see some of the digits of, I mean cubes is 1200. So maybe we can check whether it is right or wrong. That's easy. You can try it on your own. Uh, so this was the idea behind calculating the sum of cubes of the digits of a given number. Now we'll extend this problem to another problem that's called, called Armstrong numbers. So Armstrong numbers are nothing but they are those are the numbers if the sum of digits raised to an exponent equal to the number of digits returns the number itself. So if you remember in our last function, when we said uh, 153. So you remember when we run this. So first of all, we will see a good thing about this number. It's a three digit number. Okay, and we are calculating the sum of the exponent. Sum of the exponent raised to every digit. Then it returns the same number. So when we give it 153, it returns 153. So there can be one more number, maybe 370 if we try. So it's also a three digit number. It is returned 370. So basically these are the numbers when the sum of the digits raised to the power, raised to an exponent that is equal to the number of digits in the number itself. Okay, so those numbers are called these Armstrong numbers. So we will see whether the given number is an Armstrong number or not, or we'll see that the number in our case are returned as a Armstrong numbers. So uh, so for that we have already defined our exponent function, so we need not to define it again. uh, or we, as we have already discussed, we can use the power function that is inbuilt. Now we'll be defining a function that simply calculates the length of a number, because the user can input any type of number. So it's up to user, he can input any type of number. So maybe one has a choice of inputting a number that is 5 digits, 6 digits, 7 digits, and so on. So it's not up to us. So we should write a function that calculates the length of the number first. So for that we will be, so for that we will be okay. Yeah, so we'll be calculating length of the number. So we will. For calculating length, what we are going to do is we are going to initialize a number 0, and every time for every digit in the number we will add 1. Okay, so we'll calculate while this number is not equal to 0. So if number is not equal to 0, we will update the n. Okay, so we can update the n by saying n is equal to n plus 1 or n plus equal to 1. So either ways we can update the number, and then we will calculate the floor division. So let us say number is 207. So when we update this number by the floor division, we will be floor division of 10, then we will be getting next number to be 20, and we have already updated that this n is equal to 0. So we'll get the we'll get the length to be 1. Then as this number has not become 0 yet, we will further divide it by 10 we'll do the floor division, we'll get 2, and we have already updated this, so length has become 2. But 2 is also not equal to 0. It will again run, and this is how we are going to this basically function is going to return the length of the number. Then okay, we have defined a function, so it simply calls so basically it's another important point. When you are defining a function, you should define with a name which kind of defines what type of function you are writing. So you can even give a garbage name here, maybe xyz t1234 or something like that, but that will not actually define what you want to do. So basically I have defined a, I have tried to define it like length exponent sum of digits. So when we are raising length exponent to the digits, then and we are calculating the sum. It's, I mean, kind of that. You can write a better name if you try. So we'll again say, okay, if type of number is not int or less than 0, we will again call that, and then we'll again initialize that we did earlier. If the number provided is correct, I mean is as per the instruction of the developer, or the person who has written the instructions. So if so, then we will initialize sum of digits. So I have written it cube because I have just copied from above. So you can write it like, you can give some other name or something, so that does not matter here for now. So I have initialized it with some value, and I have said length of the number. Length of the number is nothing but uh, len of num, and this num we will be we will be taking as a input. So and then we will say n is equal to num. So we will be storing the value of number in some other variable called n. Then we'll say while n is greater than 0. So as with the same logic in our last problem, with the same logic, we'll say if n is greater than 0, then only this loop will run. So I will see if n is greater than 0. So in our case, I mean, if we have chosen the right number, so which is greater than 0, then it will calculate the modulus, and then it will calculate the it will calculate the I mean, it will update this initialized variable with the initialized variable plus the exponent of this modulus that we have got, or remainder we have got, raised to the power length of number. So that was the idea. uh, then, like the last function, we will update our n by doing a floor division by 10. So, as we have already discussed, if the number is 207, first iteration will return n to be 20, second iteration will return 2, and third iteration will return 0. So, basically, the length will be, I mean, it's then the length was 3, and we have calculated the exponent for the for all the digits raised to length of the number. So now we will return that you know uh, we will return this particular sum that we have calculated, and we'll also say if this number is a Armstrong number, and for that we will give a condition. This equal to, this double equal to is a conditional equal to, so it can return only two outcomes. So either if they are equal, it can return true. It can return true. If they are unequal, it will return false. So we will actually see. So okay, it's already, I have called this function, and I have given one input 9474. So we'll see whether what is the sum of the I mean sum of the exponent, I mean digit raised to the power exponent equal to length of the digit, and and if sum is equal to the number itself. So in this case, we can see that we have provided number 9474, which is equal to 9474. So it is saying is the number is Armstrong number. It is returning to be true because we have applied a condition here. So we can choose any other number which may not be, let us say I'm going to choose 12. We can choose the garbage values. We will see that it will return the outcomes as we have seen uh, in the last case. So okay, so it is returning this 5. I mean, it's the length is 2, so 1 raised to the power 2 and 2 raised to the power 2. We are doing summation. It has come to be 5. Then this 5 is not equal to 12, hence this is not an Armstrong number. It has returned it to be false. Now you should not bother about this none here because I have written a print. If I remove this print, this nuns will not come, because if I return, it will already give us these outcomes. Okay, so I think we are it's almost the time. So if we extend further, it could take the beyond our allotted time. Maybe we'll look we'll look more problems, maybe uh, in the coming class. What you guys can do, it will be shared with you, so you can try this problem 4 and 5 on your own, and you can see whether you are able to follow the logics and everything. uh, the next problem, the next two problems are, we want to find the number of zeros at the end of a factorial of a number. So let us say I say a number factorial 4. So factorial 4 will return us 4 into 3 into 2 into 1. If someone is not aware with the definition of factorial 4, it is mentioned here. You can follow this definition, and your goal is to check whether I mean, how many number of zeros are after at the end while we are computing the factorial of the given number. So if we calculate 4 factorial, it will come out to be 24. So 24 has no zero at its end, so the end digit is 4, so there are no zeros. So if you put in if you put in 4 in your number, it should tell you that the number of zeros in it are actually 0. So if it's maybe let us say 9, so if you calculate the factorial of 9, you can see that it will have 1 cross 2 cross 3 cross 4 up to 9. So although the 10 has not popped up yet, still 5 multiplied 2 will return you a 0. So this is how the algorithm I have given here. I have given you the idea how can you proceed. So there can be a very basic step, and following the basic step, we can check by using the function we have used here, the library we have used here for time. We can see that if we use a very basic idea, that first we compute the factorial of the number, and then we compute how many zeros are there by calculating the remainder, and then reducing the number by dividing it by 10. I mean, so if there is a zero in the last, when we have computed a factorial, so let us say there are two zeros in the last. So first, when you will calculate the modulus, it will come out to be 0, and when you divide it with 10, you will be left with single zero in the last. Then again you will follow the procedure. Your modulus will again be 0, so you got two zeros, and then you will reduce the number by dividing it by floor of 10, and then floor of n divided by 10. So your number will have no zeros at the end then, and then if you try to calculate the modulus, it will be non-zero. Hence in that case, you can say there are only two zeros at the end of the factorial n. So I mean, you should try this on your own. It could be a good practice problem. The idea is already presented here. the the I mean, what you can try, how do you compute the compute the number of zeros, what logic you can put in. So first was the very basic logic that we have discussed. Second logic is given here. There is a, the number of zeros would depend upon how many prime factors, I mean, what is the exponent of prime factors of the factorial, exponent of 5 basically. So let us say the exponent of 5 is 3, then guaranteed there has to be 3 zeros at the end of the factorial. And I have already discussed all those things in this approach. You can check in. Next is, we just want to calculate the number of days in February. You can follow the, if you know the idea that we think that any number that is divisible by, if the year is divisible by 4, we call it a leap year. But there are cases when this definition actually fails because this is not a sufficient condition. So let us say year 1900 or maybe upcoming 2100, though it's a long way to go, but still, I mean, that is the next century we are going to get. So but in between we got 2000, it was a leap year. So we should look for our definition further. We should look for a sufficient condition. So that sufficient condition is discussed. I would encourage you to try this problem, and your function should return whether your year is a leap year or not, or how many number of days in the February of that particular year. So basically, it's just a way of saying that particular year is a leap year. Okay, so I would like to thank you all for joining.